The geological patterns of the outer layer of our Earth are complicated. Some we understand better than others. They show the rocks that lie on or just below the surface. But finding the rocks which hold oil or gas is not simple. When we think of the whole surface of the Earth, then there is only a chance of hydrocarbons being present in about 30% of the land and the continental shelf under the sea. The white areas are sedimentary basins. Although they could contain hydrocarbons, oil or gas is present in only a fraction of 1% of these areas, a very small part of the Earth's crust, but holding a rich reward for those who can drill a well in the right place and to the right depth. We have digital information from orbiting spacecraft. With this, we can make maps of any area. Every material has its own reflective properties. The pictures not only show shape and structure, but can be programmed to reveal different types of rock, soil, and vegetation. When sandstones like this occur deep within the Earth, they could be the reservoir for oil or gas. And shale can be the source rock for oil. They were both discovered at the edge of this vast tropical plain, which might cover a deep sedimentary basin. How do we convert guesses into near certainty? This, we know, covers a sedimentary basin which started to form possibly 300 million years ago. And it might extend 500 kilometers under what is now sea. And here, too, the prize could be 3, 4, or 5 kilometers deep. Examining rock samples from the surface gives indications of the age and makeup of what lies below. Geology is an art and a science. With more data and facts, the artist becomes a scientist. A decision to survey a new area depends on a certain amount of knowledge and making a responsible but inspired guess.
That's the piece of evidence that would support the ID.
After all the available geological, geochemical, geophysical, and geographical information has been studied, the question is simply, is there a sedimentary basin? And could it be deep enough and old enough to have generated hydrocarbons? Could there be a reservoir of trapped oil or gas? A magnetic survey can answer part of this question. Aeromagnetic surveys can be made over land and sea. The bird, towed by an aircraft, picks up the minute magnetic variations in the Earth that lies immediately below. These pass up the cable to equipment in the aircraft which records them. From these recordings made over a grid of hundreds of kilometers, a computer program uses the information to plot a map of magnetic variations.
We have here a clear series of high-frequency events.
Sediments have little or no magnetic response.
They end at this point.
Some of the rocks of other types underneath are likely to be strongly magnetic. Color the results, and they can be seen clearly. Some areas are quiet and are probably the deep basins. These are analyzed, and another computer program is used to compare the patterns in the new area with patterns typical of a deep basin.
Let's try a different direction of magnetization.
Yes. Well, how about 55?
Okay.
The result in this case
Yes.
confirms the likelihood of a deep basin being present.
Okay, we'll put that horizon in now properly from the start.
Now it is reasonable to plan a much more detailed and expensive survey, a precise set of lines for the seismic party to follow. The principle of a seismic survey is the same whether the surface of the Earth is jungle, desert, city, or sea. Either on the surface of the ground or just below, shock waves are made. These travel through the Earth and are picked up by receivers. The receivers record the waves as they bounce back from rock layers several kilometers below. The length of time taken for the echoes to reach the receiver suggests the depth of the rock that is reflecting them. The echoes are changed into electrical impulses and recorded. Setting out the lines for the vibrations and the receivers is fast on open land. Here, 300 kilometers a month could be covered. In the jungle, every step is slower. The position of the line must sometimes be varied because of natural obstacles, even skirting round land owned by people who will not grant access. Then any variations in position must be noted, the information eventually being fed into the computer, which will make the necessary corrections. In a city, still practical, though the job will not be quite the same. And when the lines continue through areas of glass houses, the skills will again be different, though the principles will be the same. Every seismic operation depends on many people. Most of them will walk vast distances before any recording begins. The vibrations will be received by a robust yet very sensitive geophone. The central shaft responds to the slightest movement and changes it into an electrical signal which will be recorded on the magnetic tape. To get the best results, the geophones will be planted to a precise pattern. These patterns will be connected to a main cable that goes back to a recording van. In principle, the geophone is similar to the laboratory seismometer that records earthquakes. These are small, accurate instruments that can be used anywhere in the world, and it is practical to have them in large numbers. Their signals are recorded digitally for use with a computer. The computer is able to cross-reference the information and focus even on the changes of density in the rocks below. The circuit is checked and made ready for the recording. In a city, the ideal geophone pattern can never be achieved. The computer program will be adjusted accordingly. In the jungle, they will be using dynamite, but the connections are much the same. The information that each geophone will give is like one small piece of a huge three-dimensional jigsaw puzzle, some of whose layers are as old as the Earth itself. The lines through the jungle now cross an area of swamp. Here, holes 12 meters deep are being made. The holes are lined with plastic piping to allow a traditional charge of dynamite to be loaded. On this line, for every kilometer, there will be 40 explosions, and 1,000 geophones will record them. Groups of 5 explosions are made together. All seismic cables are connected to and controlled from the recording van.
Okay, next shot point, please.
Charge up.
Hook on, please.
Ready?
The full information is stored on magnetic tape. It will be processed and decoded later. A check is made to see that all the geophones are recording. They can now move on to record the reflections from the next set of explosions. In the desert, 2 ways of making the initial vibration are used. Dropping heavy weights is much quicker than dynamite and is very efficient in sand dunes and where the sand is loosely packed. This is vibrosize. After the pad is lowered, it is pressed against the ground using the whole weight of the truck that carries it. It is then vibrated, and the vibrations are, of course, picked up by the geophones. This is again a very quick method, and many kilometers can be covered each day. Vibrosize works best when the land is firm. It gives as much information as dynamite or the weight drop. Vibrosize is also best for the city, though it needs to be done at night when there is less heavy traffic and other machinery making vibrations that could interfere with the recording. A torch, shone at road level, checks that the pressure has not damaged the road surface. Vibrosize and weight drop machines are too big for a glass house, and they wouldn't do the plants much good. So, surprisingly, it's back to dynamite. Open the windows, and a series of small charges can now be controlled so as not to affect the plants or the glass. Dynamite is no longer used as a source of seismic energy at sea. It has been replaced by the air gun, which releases short bursts of highly compressed air underwater. These air guns are towed immediately behind the seismic ship. At the same time, the receivers, hydrophones, are in a cable towed way behind it. These pick up the reflected vibrations from beneath the seabed. The vibrations from land and sea are now sorted out by computer. Each trace is the recording from one geophone. Many geophones, many traces forming a seismic line. Although the pattern that first appears makes no geological sense, the use of modern computers now enables work to be done in seconds that used to take weeks. Removing interference and unwanted noise and the correlation of information from one geophone to another is now relatively simple. The computer reprocesses the information stage by stage until a picture emerges where a seismologist will select important layers that must be converted into maps. Interpretation is a marrying of knowledge and experience. The interpretation is put onto another computer so that the time which the signals took to reach the geophones can be converted into depth. This tiny machine continuously works out problems which in the days of hand calculations would have been practical at only 1 or 2 points. The information from the computer can now be used in many ways. One is to produce maps. Three-dimensional pictures of individual layers that lie deep in the Earth can be viewed from all sides to help our understanding of its structure. Machines and computers can be used to acquire and process geological information from beneath the Earth. But it is the human brain that must finally interpret that information and decide just where to locate a new well that has the greatest chance of striking oil or gas.
Whether under sea or land, the search for oil is ultimately a gamble. For no matter how thoroughly geologists and seismologists have surveyed the area, the only way to find a new oil field is by drilling an exploration well at a cost of millions of pounds. On the rig, the geologist keeps a log of each layer of rock as it is drilled through. He compares his log with the rock structure predicted by the survey. After 10 weeks of drilling, they're approaching the likely oil-bearing strata. So the geologist has called out the petroleum engineer from the mainland. The geologist first locates the oil. Then the petroleum engineer must find out how much is there, if any. For there's only a 25-to-1 chance of success.